Diagonalization, we are going to start with an n by n matrix A that is non-deficient, right? By non-deficient, we mean that A has enough n-independent eigenvectors, say x1, x2, up to xn. Each of the eigenvectors is a column vector, so we can put them together. That will help us form a matrix that we denote as Q. D is the diagonal matrix. So that means that D only has entries on the main diagonals. Otherwise, you just fill in zeros. If x1 is the first column for Q, then the corresponding eigenvalues to x1 will be the first entry on the diagonal. If x2 is the second column for Q, then the corresponding eigenvalue of x2 is going to be the second entry on the diagonal. And similarly for the last xn, its corresponding eigenvalue is going to be the last entry on the main diagonal. So in other words, we keep the order of the eigenvalues and the eigenvectors the same as in Q and in D. The nice thing is that if you set up Q and D in this way, then A is going to be equal to Q times D times Q inverse, provided that A has enough n-independent eigenvectors. If A does not have enough n-independent vectors, then the existence of the square matrix Q is none, right? That means theorem 5.4 is not valid, right? The process in which we write A as the product of Q, a diagonal matrix, and Q inverse is called the diagonalization. All right, so let's consider one example. Diagonalize the following matrices if possible. If you still remember, A and B were the matrices that we have already shown for the eigenvalues and the eigenvectors. For A, we were able to get lambda 1 being 1 and lambda 2 being 3. For lambda 1 being 1, we were able to obtain two independent vectors that form a basis for the lambda 1 eigenspace. So x1, negative 1/2, 1 and 0. And x2, 0, 0, 1. And we were able to find one independent vectors that form a basis for lambda 2 eigenspace, x3. So all this information says that A has enough 3 independent eigenvectors. In other words, A is non-deficient. And so we can diagonalize A. Remember, A is a 3 by 3 matrix, right? So it's got to have enough 3 independent vectors. If you are working with a 5 by 5 matrix, the matrix has to have enough 5 independent eigenvectors. Then we set up Q. Well, Q is going to be just putting x1, x2, and x3 together. And so you are going to get a 3 by 3 matrix that is negative 1/2, 1 and 0, 0, 0, 1, 1/2, 0, 1. The D, now let's look at S1. What is its associated eigenvalue? That is the number 1. Now when we look at x2, its associated eigenvalue is still lambda 1. So you've got to put 1 here. For x3, the associated eigenvalue is 3. So you put 3 here. And then you just fill in 0 into the other places. Right? And this is the diagonal matrix that you have. By theorem 5.4, A is going to be equals to Q times D times Q inverse. Right? We often don't need to compute the inverse until we have to do so, because computing the inverse requires a lot of time. So we'll try to avoid it as much as possible, unless we have to run into it. Otherwise, we don't compute it. Now for matrix B, Last time when we solved for the eigenvalues of B, we found two eigenvalues, lambda 1 being 3 and lambda 2 being 5. For the eigenvalue 3, we were able to find one independent vector that we denoted as x1, and that was 1, 0, 0. For lambda 2, 5, we found one independent vector x2, and that was 3/4, 1/2, and 1. This means that B, which is a 3 by 3 matrix, does not have enough 3 independent eigenvectors. In other words, we say that B is deficient. Because we don't have enough 3 independent vectors here, we cannot set up the Q, and so the diagonalization is not obtainable. B is not diagonalizable. Let's consider example number 2. Compute A to the power 100. So we know that A is QD Q inverse. This implies that A to the power 100 is QD Q inverse 100 times multiplied together. This is the same as you multiply QD Q inverse with QD Q inverse with QD Q inverse. Alright, and then QD Q inverse 100 times. Alright, so if you pay attention, then you will see you can use matrix multiplication associativity to combine Q inverse and Q inverse and Q. And right here, if you write something more after this, then it's gonna be a Q. So you can combine the Q inverse and the Q after that. Before you get to the Q here, in front of it, there should be another Q inverse. And every of them, when you combine together, is going to produce an identity matrix. Right? For this one, if you write one more factor after the factor here, then the Q inverse will combine with the Q, and that's going to generate the I for you. For this one, if you write one more term in front of it, there should be another Q inverse that will be combined with the Q here, and that will generate the identity matrix. And then D and then Q inverse. Now you know that multiplying the identity matrix is kind of doing nothing, and so you can reduce the computation to Q, D, 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 dot, dot, D, Q inverse. And this D happens 100 times. And so in other words, the A is going to be equal to Q times D to the power 100 times Q inverse. When you compute the power of a diagonal matrix, you actually just take the power, apply it onto each of the entry on the diagonal. Remember, Q is negative 1/2, 1, 0, 0, 0, 1, 1/2, 0, 1. D was just 1, 1, 3. And so D to the power 100 is going to be 1 to the power 100, 1 to the power 100, and 3 to the power 100. Elsewhere, you're going to get 0. And then you know from here that you have to compute Q inverse if you want to find the final answer. Right, so this is the identity matrix. And so this should give you the Q inverse. Now we substitute everything into the star equation that we left in the middle here. Right? We are going to get A to the power 100 being Q times D to the power 100, and then times Q inverse. And of course, we use associativity. We multiply the first two. If you do the computation correctly, multiplying the first two will give you this. And then you multiply with the Q inverse. The final answer is going to be 3 to the power 100, 0, 2 times 3 100 minus 1. The second column will be 1/2. 3 100 minus 1. 1. 3 100 minus 1. 0 0 1. Next, I'm going to prove theorem 5.4. A has n independent eigenvectors x1, x2, xn, and each of the eigenvectors is associated to an eigenvalue lambda 1, lambda 2, lambda n. What it means by being eigenvectors and eigenvalue is that if you multiply A by x1, then you are going to get lambda 1 times x1. A times x2 is just like giving x2 a scale lambda 2. And similarly, A applied on xn is just like you stretch or shrink xn by a factor lambda n. Now let's consider A multiplied with the matrix Q. It's the same as you multiply A with the matrix whose columns are x1, x2, xn. That's how we set up the Q, right? Now, by matrix multiplication, we know that multiplying two matrices together is the same as multiplying the first matrix by each of the column of the later matrix. So this is going to be the same as A multiplied with the first column, A multiplied with the second column, and then A multiplied with the last column. Then this is going to be the same as lambda 1 times x1, lambda 2 times x2, lambda n times xn. This is the same as multiplying the matrix whose columns are x1, x2, xn by the diagonal matrix lambda 1, lambda 2, lambda n, and zeros elsewhere. Why is this the same as multiplying this? Right? The reason is, again, by matrix multiplication. If you multiply this matrix by this matrix, you end up multiplying the former matrix by each of the column of the later matrix. So if you want to find the first column for the result, then this is the same as you multiplying the matrix x1, x2, xn by the first column, lambda 1, 0, and a bunch of 0. Now, by matrix vector multiplication, this is going to be the same as you are going to combine the columns of the matrix as a linear combination where the scalars comes from the entries of the column vector. So this means you will have to multiply lambda 1 with x1, 0 with x2, 0 with x3, and 0 with xn, and then add them together. All the letters are going to be just 0, and so at the end, this is lambda 1 x1, and so lambda 1 x1 is just the result of multiplying this matrix with the first column. Similarly, if you multiply this matrix with the second column, what happens is that you are going to get 0 times x1, lambda 2 times x2, 0 times x3, and then 0 times xn. That's why you only get lambda 2 x2 here. And similarly, you are going to get lambda n xn for the last column. And this is going to be just Q. And we denote the new one up here as the D, the diagonal matrix. So we have successfully written A times Q as Q times D. Now we really want to multiply both sides by Q inverse so that AQ Q inverse equals to QD Q inverse. This is going to give you I, and A times I is just A, and you get theorem 5.4. But the question is, are we sure that Q is invertible so that its inverse exists? Up to this step, we haven't proved that the Q set up in that way is an invertible matrix. All right. What if the Q set up in that way is not invertible? It means that the Q inverse does not exist. And so writing Q inverse is just like a joke, right? We write something that does not exist. So all our argument will be invalid if Q is not invertible. So we got to prove that Q is invertible, right? The answer is yes. Proof for Q being invertible is quite simple. Remember, Q is set up by putting the eigenvectors x1, x2, xn together. And we know that the column of Q's, which are x1, x2, xn, is independent. The columns of Q are independent if and only if the rank of Q is n, which is the number of columns. This is equivalent with Q is invertible. That means that Q inverse exists, and we can use it in the above argument. Now let's consider example number 3. Find the two functions x1 and x2. These are the two functions in terms of the time variable t. Right. And we have the differential equations. x1 prime equals 3x1 plus x2. x2 prime equals x1 plus 3x2. With the initial conditions, x1 of 0 equals 5 and x2 of 0 equals 3. We have the equation. Isn't it the same as writing the column x1 prime, x2 prime equals to the matrix 3, 1, 1, 3 times x1 and x2. Let's denote this matrix, the matrix A. Denote the state vector or the vector of the functions x1 and x2 as capital X. Then this is the derivative d dt of the matrix of x1 and x2. And so we usually write d dt of capital X equals A times X. And for simplicity, people will write x prime equals A times X. So in order to solve this system of linear equations, first we are going to find all the eigenvalues and eigenvectors of A. And so you see that either lambda is the first value 2 or lambda is the second value 4. Now our next step is to find all independent vectors associated to each of the eigenvalues that we have here. First, for lambda 1, the lambda 1 eigenspace is just the span of that vector negative 1, 1. And we can go ahead and name this one x1. For lambda 2, the lambda 2 eigenspace is just the span of 1, 1. And we can name this one capital X2. So the next step is to diagonalize the matrix A. A produces enough independent vectors to be called non-deficient. And so A is diagonalizable, which means A can be rewritten as QD Q inverse, where the Q is just putting the axes together. And that obviously be the following matrix, negative 1, 1, 1, and 1. X1 is associated to lambda 1, so this should be lambda 1. What is it? Lambda 1 is 2, so you can go ahead and write 2. Right. Now for x2, what is the associated lambda value for that vector? x2 here, lambda 2, that is 4. So you put 4. Because this is a diagonal matrix, so we have 0 elsewhere. All right, so back to the system of equation. Capital X prime equals AX. Now A is QD Q inverse. So I'm going to multiply Q inverse to both the left and the right hand side. So this is going to give me Q inverse X prime equals to, this is going to be the identity matrix. So I'm not going to write it again because I know that multiplying the identity matrix is like doing nothing. So D Q inverse and X. Although I have not computed the Q inverse, I don't know exactly what it is, but I know this is just a 2 by 2 matrix with 4 numbers in it. So Q inverse times x prime is the same as Q inverse times x on derivative. And on the right, I'm going to group the Q inverse and the x. Well, then I'm going to let Z being the Q inverse times x. At that time, the whole thing on the left would simplify to just Z prime. On the right, we are going to have D times Z. We don't know what is happening here, but at the end, it's going to be just some function of Z1 and Z2 that we usually just write Z1 and Z2 for simplicity purpose. So Z is going to be some Z1 and Z2. That means that Z prime is going to be just Z1 prime, Z2 prime. And so here we are going to have Z1 prime, Z2 prime equals to the diagonal matrix 2 and 4 times Z1 and Z2. So this means that you are going to have Z1 prime, Z2 prime equals to 2 times Z1, 0 times Z2. So the first entry will be only 2Z1. Similarly, the second entry will be only 4Z2. And so this is equivalent with solving the system of two very simple differential equations. Z prime equals 2Z and Z prime equals 4Z. This is equivalent with having Z1 equals to some constant C times E to the 2t and Z2 some constant C times E to the 4t. Now we'll never know whether the constant here and the constant here are the same, so we should not use the same notation. We should use C1 and C2. So this implies that the matrix Z of functions, or the vector function Z, is actually just C1 E2t, C2 E4t. But we need to find the x, right? Remember, Z is set to be Q inverse times x, right here. So this means we have Q inverse times x equals to C1 E2t, C2 E4t. Then we are going to multiply Q to both sides to Q off the Q inverse here. And we are going to get the x equals to, now the Q, we know the Q. What is it? It was known to be negative 1, 1, 1. We computed it when we diagonalized the matrix A. Right, so now we are going to utilize that. And we multiply the Q with C1 E2t, C2 E4t. This is going to be equal to negative C1 E2t plus C2 E4t and C1 E2t plus C2 E4t. Remember, x is just another way of writing x1 and x2 in column. So that means you have identified your x1 to be this guy and x2 to be the second one. So this is equivalent with, we have found the x1, in other words, x1 of t variable is negative C1 E2t plus C2 E4t, and x2, which is a function of the t variable. If you want to be precise, you should write x2t, C1 E2t, C2 E4t. All right, so how can we identify the exact function for x1 and x2, because we still have arbitrary constants C1 and C2 here? We are going to utilize the initial condition. x1 0 equals 5 and x2 at 0 equals 3. What this means is that at the beginning, when t is 0, the value for x1 is 5. So if you substitute t being 0, 0, 0, then x1 is 5. And if you substitute 0 for x2, then x2 is going to be 3. So this is equivalent with 5, the value for x1 is equals to that when t is set to be 0. And 3, the value for x2 when t is set to be 0 is going to be c1 e2 times 0 plus c2 e4 times 0. Now, when the exponents are zeros, the exponential function will give you the value 1. So this ends up being the system of linear equations of two unknowns c1 and c2. And so you can easily solve for c1 and c2. So c1 is -1 and c2 is going to be 4. Now, from this equation, you can just substitute c1 and c2 as the values here. So you are going to have, and this is the final answer. Previously, we were doing the diagonalization process. We were able to rewrite any non-diffusion matrix A as QD Q inverse. And when we do so, remember, you find all eigenvalues. For each eigenvalues, you find all independent vectors associated to that eigenvalues. Then you repeat the process for the other eigenvalues until the last one. So you have the first set of independent vectors that is associated to lambda 1. Right? Then you have the second set of independent vectors associated to lambda 2. The interesting thing is that when we combine these independent vectors together, we get a larger set. And that larger set is independent. That's the surprising thing.